Okay, in today's class, we're going to talk about how to model a time-dependent structural mechanics problem. So again, when you have something that's time-dependent, that means that over time, something like the boundary load will change. Okay, so you'll see that I have COMSOL already opened here. So I'll go ahead and click on the model wizard. And for this model, we're just going to do model a 2D cantilever. So I click on 2D. And again, the type of physics that we're going to use is solid mechanics. So I'll add that to the model. And what we're going to be doing today is the type of study is going to be a time-dependent study. Okay, so I click on time-dependent and press done. So again, time-dependent means that the load should change with time. As time changes, the load changes. Okay, so we're going to try to model a simple 2D cantilever. So I'm going to right-click on geometry, and I'm going to build a rectangle. And let's go ahead and make this rectangle 5 meters long, and let's say 0.5 meters high. So I'll press build selected, and there we go. We have a simple cantilever. Okay, now that we have our cantilever geometry built, let's go ahead and add some material properties. So I'll right click on materials and add a material. And from our built-in library, I'll just select this material as nylon. Okay, so a nylon plastic. And I'll right click on that and say add to component. And so now it's added the material properties to this geometry. I'll go ahead and close the material library. Okay, and then moving on to the solid mechanics, I'll right click on solid mechanics to set up boundary conditions. So the first boundary condition I'm going to set up is going to be a fixed constraint. So let's say since we're trying to model a cantilever, that this side of the cantilever is fixed against the wall, and we will put the load on the other side of the cantilever. So to add the other boundary condition, I right click on solid mechanics, add a boundary load, okay, and we're just going to put the load on this end, the very end of it. Okay, if I can click, there we go. So you see in blue, just the very end face, we're going to apply a load to the end of that beam. And since this is going to be a time-dependent model, we need to set up a variable, and we need to call that variable, give it a name. So I'll give it a name called load, and load is going to be a function of time. Okay, so load of t will be my variable. Well, now we got to tell COMSOL what's the data for each time point. So to do that, for a time-dependent model, I right-click on the global definitions, and here we're going to add an interpolation, okay, which will have the different time points from t equal to 0 all the way up to 8 seconds, and it'll interpolate for us the in-between steps. So I click on interpolation, okay, and for the function name, we'll call this load, okay, and at t equals 0, let's have f of t, or the load, just be 0, okay, so it starts out with a 0 Pascal load on it. Okay, and then 1 second later, on that face, remember we selected the edge, the face over here. We'll go ahead and apply a load to that. In the y-axis, it's going to be negative 500 pascals, or newtons per meter squared. Okay, so that's going to be pushing down on this face. And then at t equal to 2 seconds, let's have it hold that, negative 500 Pascal, or newtons per meter squared. And then at 3 seconds, let's have this all of a sudden start pushing up. So the positive 1000 pascals in the y direction. And let's hold that for a second. So at t equal to 4 seconds, we'll just say we'll hold it at that 1000 pascals. Okay, and at t equal to 5 seconds, let's reduce the upward load to pushing up on this face, or on this edge, to 500 pascals. And at 6 seconds, let's just hold it there for a little bit. And then at 7 seconds, we will let's push down in the negative y direction, going negative 500 pascals. And let's end at t equal to 8 seconds, just holding it there at with a load of negative 500 newtons per meter squared, pushing down on this end face. So we just manually typed in these data points. So at each second, at t equal to 1 second, 2 seconds, 3 seconds, at each time point, we just typed in the load. But I will say that there are, so that's one option. You could type in the load, the function here, or if you have data collected from something, from actual biomechanics study, or if you have data collected from some other device, you can import the data. So say you had an hour's worth of data and you wanted to model all of that, you wouldn't have to type it all in. You could import that data. Okay, but for the sake of this example, and just for to keep this example simple, we're just doing a simple example where we're just typing in the first 8 seconds of data as we put a load on the edge of this cantilever. And we can view that data, okay, and by clicking on plot. And this is what we would expect. Okay, so remember at t equal to 0 seconds, there's no load, but because we're interpolating from 0 seconds to 1 second, we get a negative 500 Pascal load on the end of the face, and then we hold it for 1 second, and then all of a sudden we push up from between 2 seconds to 3 seconds. We push up with 1000 newtons, hold it for a second, and then we let go of some of that pressure to 500, hold it for a second, and then we return to this negative 500. So you can see here's our data, here's the load, and we are connecting the data. We've just given the computer time steps at each second and the corresponding load, and it's interpolated in between those time steps, and the type of interpolation we've done here is a linear interpolation. We'll note that you can do different types of interpolations. This linear interpolation kind of makes a quick change between the loads all of a sudden. If you wanted it to be a little bit smoother, you could do something like a cubic spline interpolation. If I update the plot, you'll see it's now interpolated it, making it more smooth. Okay. But for this example, we'll just stick with a linear interpolation between the data points. Okay. And then we'll go ahead. So we set up the load variable. Okay. In the boundary load, we've already told it in the y-axis. The load on this face is going to be the function load of t as a function of time. So there we go. That's how we set up our time-dependent model. And I'm ready to move on to the next step, which is to create a mesh. And I'll just use the default mesh settings. And so I'll just click Build All. You can see I have my finite elements and my mesh built here. And in the study, I'll click on the time dependent. And in the time range, I'm going to have this study go from 0 seconds all the way up to, let's have it go up to 8 seconds. And we're just going to have it go in steps of 0.1 second. Okay. And I'm going to want to plot the results while solving. That way we can watch it. Okay. So there we go. We've set up a time-dependent model. We're going to run this model for 8 seconds. And so I go ahead and click on Study and then click on Compute. And this model should compute. Okay, so here's the first step. And then here's the next step where it pushes it up. And then at t equal to, later it pushes it down again. And you'll see that the model has finished solving, and it'll show the time steps. Okay. So this is the time at 8 seconds. Okay. And we can play that by clicking on Player. Okay. If with this plot highlighted, again, this is my stress default plot. And there's a deformation plot overlaid. So with stress highlighted here, if I wanted to make a player out of that, I could click on Player, and it'll go through and play it. Okay, it's playing it, and notice we can see when we're pushing down, and we can see when we're pushing up, and then when we come to pushing down again. Okay. And let's say we wanted to plot this data. Okay, so let's take a look at how we would plot this data. So if I right click on results, let's go ahead and add a 1D plot group. Okay, and to this 1D plot group, let's add a point graph. Now remember, point graph means it's going to get the data from a point. Okay, and we have to define what point. So this is not a line graph. If we wanted to get the data from a line or an edge, then we would select that. Instead, we're trying to get a point graph. So trying to get the data from just one single point, and we'll pick a point on the tip of the cantilever. So I click on point graph, and let's go ahead and select the tip of the cantilever here. You see how it turned blue, and see how it showed up in this selection. So that's point number 4. And let's try to model the displacement in the y-axis only. Okay, so I'll just go here to the solid mechanics, the displacement, and let's just look at the displacement in the y component. So I'll double click on that, and it's going to add that as v, and the units are going to be in meters. Okay, and so I'm ready to plot, so I'll go ahead and click on plot, and look, here are the results. Okay, so at t equal to 0 seconds, as we would expect, there's no displacement because nothing's getting pushed. But as time goes on, and from t equal to 0 seconds to 1 second, as you recall, we push down with negative 500 newtons. Come here to the definition. As you recall, we push down with 500 newtons. So as we would expect, the beam gets deformed or displaced or pushed down in the y-axis and then held there for 1 second. Then at t equal to 3 seconds, all of a sudden we start pushing up with 1,000 pascals. So we would expect the results, okay, so this is the displacement field for the y component, all of a sudden starts pushing it up, and it starts bending up and is held there for a second. And then we reduce the load to 500, and then we switch and start pushing down with negative 500 pascals here. So this is how you would. This is how you could set up a time-dependent model, and in a simple 2D time-dependent model, and model the deflection or the displacement of that model. And you can visualize these results here too if you with this 1D plot group highlighted. Okay, if you just click on player, it'll go through and play those results. So this is what's happening as time goes by on the displacement of the edge of the cantilever. Okay, and again, don't forget to make sure that your axes are labeled. So this is the displacement field in the y component, and in the x-axis is time. Okay, so that's how you set up a time-dependent model. In the next class, we'll discuss a little bit more on how to make this model a little bit more complex. Okay, but for now, this is a good start. This is very basic how to set up a time-dependent model, and we'll go ahead and end there.